In this fourth video, we will speak about system of equations and inequations. I was hesitating whether to present a proof of the following statement, and eventually I decided not to. You can find the proof in the document tab.pdf, which will be linked. And the statement, which is highly non-trivial, says that a finite set of Boolean functions over atomless Boolean algebra has a common non-zero if and only if none of the functions is identically zero. So to say it more precisely, exist a couple of variables such that this is logical conjunction, a finite one, gi of x not equal 0. This is true if and only if this is true. We get a remarkable case where existential distributes over conjunction. This holds only in this case. So first note that everything here is negative, everything does not equal 0. And we make the assumption that we are in an atomless Boolean algebra. That's very important. This is not true in general Boolean algebras. First thing to notice, in the two-element Boolean algebra, if you are equal 0 or not equal 0, it's pretty much symmetric. If something not equal 0 is the same as saying that its complement equals 0, but is only in the two-element Boolean algebra. This is not true in other Boolean algebras. And especially over infinite Boolean algebras, handling negative constraints is much more difficult than positive constraints. So you can see a proof of this statement in the document TABA. It's a highly non-trivial statement, of course, but here we will rely on the proof appearing in TABA, which is a new proof, by the way. It is also a new statement. It was already proven by other authors to my understanding, only for simple Boolean functions, but here we refer to Boolean functions in general. And in all sources that I saw that put a claim similar to this, I was able to find bugs and counterexamples. So as far as I know, what you are going to see in TABA is the first closure of this subject. Now, let's use Rudiano's terminology, which I commonly use. Rudiano wrote the book Boolean Functions and Equations. It is a book that is unfortunately very hard to get, but it is the best source for the subject. For what I said in previous videos, but what I'm going to say from now on is pretty much all novel and is also protected from commercial use by being patented by the company IDNI. So to use Rudiano terminology, we define elementary generalized system of Boolean equations. So it looks like this. You have a bunch of positive constraints, some Boolean function equals 0, and a bunch of negative constraints, some Boolean functions not equal 0. All finite. Whenever we speak about system of equations, there are only finitely many equations. This statement is trivially false if we allow infinite system, because you can simply say that all elements are different from some certain element, and it's of course going to be false. All atomless Boolean algebras are infinite, and therefore you cannot say this in this finitary setting. The first step of dealing with elementary GSP is what I call squeeze the positives It means that you have a single positive equation and many negative equations. And this is possible because if fx equals 0 and let's say hx equals 0, this is the same as fx union gx equals 0. More generally, any bunch of elements in Boolean algebra, they are all 0 if and only if their union is 0. So very easily we can get a single positive and many negatives, and the negatives cannot be squeezed into one. It is very clearly impossible, but I guess it will be clear later on why not. In general Boolean algebra, or at least in infinite Boolean algebras, it is impossible to squeeze them into one. Now, let's try to eliminate quantifiers one by one. So, without loss of generality, consider the univariate case. Because here, this thing is prefixed by exist x, and the coefficients in f and g may depend on the rest of the variables. But at the scope of exist x, we can look at it as a univariate function. Now we use the general solution we saw above. All zeros of f can be written in this form. So we can, without loss of generality, write here x plus fx, because, sorry, can write in both places x plus fx, because we are only interested in zeros of f. Oh no, I made another mistake. It should really be like this. This is Boole's consistency condition that says that f has a 0. And here we want g to be 0 on some of the zeros of f, on at least one zero of f. So we obtain this form. Now, see what happened. This exist x is now pushed here. It no longer appears here. And now we use this result. This tells us that we can push this quantifier inside. And now what does it mean that exist x, that this is not 0? That the function is not identically 0? Well, it means that the union substituting 0 for x and 1 for x is not 0. So I can write it like this. I can delete the quantifier. Here I substitute 0. Here I substitute 1. So this is going to be 1 plus something, which is the negation. We obtain this form. And we got this beautiful result. This system has a solution if and only if this is true. So we managed to eliminate an existential quantifier, and by that we managed to eliminate all quantifiers by negation and conversion to DNF. Because in the language of Boolean algebra, this is going to be one DNF clause. Of course, existential distributes over disjunction. Therefore, what I showed you here is a complete algorithm for quantifier elimination over atomless Boolean algebras. 2 remarks. It is easy to show that there is an even much nicer form, and it looks like this. In this form, I only need to multiply by the negation of f, and I don't need to perform substitution. This exist x will expand into, to say that the function is not identically 0. It will, of course, expand like before to this expression, which is, again, a more convenient expression because there is no composition here. So we get this even more beautiful result. To move from here to here, you simply write f and g with their coefficients. You simplify this expression while taking into account this part. And then some elements will become 0, and then you will get this very nice expression. Second comment is that I said that this is quantifier elimination in the theory of Boolean algebra, but there is more to it. The standard theory of Boolean algebra has the signature conjunction, disjunction, conjunction, disjunction, complementation, 0 and 1. If this is your signature, then you can express only simple Boolean functions. But here we solved it for all Boolean functions, not only simple Boolean functions. So here we assume that the theory of Boolean algebra is interpreted in a fixed structure and that there is a constant symbol in the signature interpreted in the BA for each BA element. So in this theory interpreted in specific Boolean algebra, I can explicitly refer to each Boolean algebra element. And I can have a complete decision procedure based on quantifier elimination using these formulas.